At AI Day 2022, my favorite part of the entire presentation was something that John Emmons did, and I've been holding off on talking about it because it's so cool and it's so aligned with some things that I've been working on that it's kind of a treat to get to talk about it. Let's take a look. Hey y'all, it's Dr. Know-It-All. I want to talk to you today about lanes and finding lanes and driving on lanes. And I know that doesn't sound very interesting at all, but it's amazing what they're doing, and John Emmons presented it. I don't think this is the correct title anymore because Omar, or Holmar's catalog, said that he's now taken over what Andre Karpathy used to have. But anyway, as of January 1st of 2022, he's the Senior Manager of AI and Vision at Tesla Autopilot. So I believe his title might have changed, and he might actually have a better title now, but who knows? Anyway, that's what I could find on his website and on his page and everything. And of course, I'll put links to all of this, including the AI Day presentation, down in the description below. So check that out if you're interested. So today I want to go through about a 7-minute section of the 3-hour and 20-minute or so presentation that was given at AI Day, which is the reason why I'm never going to get done presenting topics about this. But in this section, John Emmons, as you can see, talks about lanes and objects. And by the way, again, on the very, very far left, the first row that you can see, that sort of gray head in the front on the very far left, that's me. This is the back of my head. So there you go. I was like, I thought it was me last time, and now I'm absolutely sure it was me because I've actually watched the video and watched me nodding and all of that kind of stuff that I do. So anyway, that's very cool. But anyway, I'm going to play through parts of this stuff. The whole thing is really amazing, and I'll explain why I think it's so cool and that I've actually got a little pat on the back for myself for all of this stuff. But Ashok Elluswamy actually talks to John. They have a little bit of an outtake where the two of them have a discussion about it that's obviously unscripted, and it's really, really cool. So we'll get to that. But first, we're going to get the background and why this is important and why it's such a difficult problem.
Hi, everybody. My name is John Emmons. I lead the Autopilot Vision team. I'm going to cover 2 topics with you today. The first is how we predict lanes, and the second is how we predict the future behavior of other agents on the road. In the early days of Autopilot, we modeled the lane detection problem as an image space instance segmentation task.
Okay, so let's go ahead and just stop that right there. So we've talked about this a lot, and I've done a whole bunch of other videos on this, but image space segmentation basically means you're dealing with the 2D image. So what you're looking at right now on whatever screen you're watching this on, that's a 2D image space. So if you imagine seeing a road, just like they're showing in this picture here, they're seeing a road as a 2D image space. So it's a whole bunch of pixels. And what you would do is you would say like, oh, here's some white pixels going along like this and making a curve. So that would be the center line, and here's some yellow ones on this side. That's the sideline. So we can start to figure out where lanes are and everything. And I don't know this for sure, but I think that the stack that is running on the highway might still be primarily using this. So this works pretty decently on a highway, which is the reason why highway autopilot has always been so much better than city auto. Well, one of the reasons why it's so much better than city autopilot is because lanes are relatively straightforward. It's like they're really, really clearly marked, and they go for long distances in straight lines. They don't have lots of turns, things like that. So you can do this in image space, and it's actually pretty reasonable. And if I move myself out of the way over here, you can see that they had a relatively straightforward processing path that they would go on. So they would take their input image and they would use a RegNet. And here's a quick definition of RegNet. It's a flexible network architecture for computer vision. And just in case you didn't happen to know, again, I'll leave a link to this in the description if you want to read more about it. But the important part here is that RegNets are very flexible for visual tasks. They're more flexible than the sort of classic ImageNet. And it's funny to talk about classical things that are only 10 years old, but ImageNet was developed about 10 years ago. So it's basically, at this point, it's old school stuff. So RegNets are a more kind of flexible, expanded version of something like ImageNet. So anyway, you take your input image, just a still frame from one camera, you feed it through a RegNet, and then you put it through an FPN. And again, if you want to look here, this is the definition of a feature pyramid network, or FPN. You will also see bi-FPNs, which are bidirectional FPNs. And if you look down in the bottom here, again, I'm kind of in the way of all of this stuff, so I'll try to move myself out of the way here. You can see what it can do is segment out this tennis player from the background and also the tennis ball and her tennis racket, as well as like some, I don't know if those are goat or sheep, whatever that is, human being, other people, tents, background, grass, etc. So what an FPN can do is it can segment out a scene in a very efficient manner. So anyway, we feed that still image through the RegNet, through the FPN, we get a fully connected layer, which is just a dense neural network layer. And then from that, we can get the primary lane, which is the lane we're driving in up here. We can get the adjacent lane, which in this case is the lane to the right. We can also get forks, special instances of forks and merges. So those would be lanes that split off like this, lanes that come together like this. And basically for a highway, that's approximately all you need to know. You need to know it in many different lighting circumstances and rain and possibly snow and hail and clouds and sun and nighttime and daytime and all of that kind of stuff. But basically it's a fairly straightforward thing. And so you can use a fairly straightforward architecture to make that work. But as we're about to find out, it's a lot more complicated on city streets, as you might imagine, I'm sure, if you've driven around city streets before.
Our network was super simple though. In fact, it was only capable of predicting lanes of a few different kinds of geometries. Specifically, it would segment the eagle lane, it could segment adjacent lanes, and then it had some special casing for forks and merges. This simplistic modeling of the problem worked for highly structured roads like highways. But today we're trying to build a system that's capable of much more complex maneuvers.
So if the two images on the left don't terrify you, then I don't know what will. So you can see we've moved from a very, very simple architecture to, in the top left case, we have 6 different main thoroughfares all intersecting, and each of those has multiple lanes in it. So that's incredibly complicated. And the bottom left is even more terrifying. I'm not exactly sure how to count how many lanes are in here because there's lanes everywhere. There's a little sort of boulevard thing in the middle that looks like you can do U-turns on. There's middle sections. It's absolutely nuts. So when you start looking at images like this, you can see how a car could get incredibly confused by, you're like, oh, it's just a lane thing. How big a deal is that? Well, this shows how ridiculously complicated lane following can get when you get to very complex intersections. And then you can see the top right image said, even a simple turn breaks the structured lanes. So the green lines that are going forward, that's the idea. That's the lane thing. It's like, oh, this is where I'm supposed to be going. But making a right or a left-hand turn, it has no idea where to go. So it doesn't know, it doesn't understand these lanes. It doesn't know how to turn, doesn't know how to do any of this. And then of course, hopelessly insufficient in complex intersections like we're seeing on the 2 left-hand images. So the old network was not up to snuff, and they needed to be able to do something to overcome these problems. And the solution they came up with is genius.
Specifically, we want to make left and right turns at intersections, where the road topology can be quite a bit more complex and diverse. When we try to apply this simplistic modeling of the problem here, it just totally breaks down. Taking a step back for a moment, what we're trying to do here is to predict the sparse set of lane instances and their connectivity. And what we want to do is to have a neural network that basically predicts this graph, where the nodes are the lane segments, and the edges encode the connectivities between these lanes.
Okay, so there's a lot going on here. So if you remember, the original thing was taking images and it was segmenting those images out in pixel space, in raster space, and figuring out where everything was. Now, as we've talked about many, many times, the vision system now is able to create a full 360-degree video sequence. And this video sequence lives in more of a vector space than it does in a raster space. In other words, it's identifying objects and things like that, but that still doesn't help us with lanes ultimately. And the problem with lanes is that their geometry is not like kind of discrete. Like if you take a car, right? So any of these vehicles that are in this image, those are discrete objects. You can segment the scene out and say like, that's a car. And this is not car. This is other things. But look at these lanes. These lanes move and they turn and they go through intersections where they're gone. There is no lane line in the middle part. The blue lines with all of these arrows is actually projected paths through the middle of the intersection where there is no clue about where the car is supposed to drive. So it has to be able to get from, like, let's say the bottom right near where my video is, up through the intersection to the other lane that's the appropriate lane. And it has to be able to do that without wiggling around all the way through the intersection. That's a really complicated problem, and it's a dense problem because all of these lanes and all of this stuff is a multitude of information. So what Tesla's goal was to take this really, really dense tensor, and the tensor just means it's a representation of all of the lane information in the scene. And that's very, very dense. Every single point and all of that, if you gridded it out, would be immensely complicated and too taxing for the computer. So what they're trying to do is take that really, really dense information and turn it into sparse information. So as John said, what they're trying to get is each node is a lane, and then the edges are the connecting tissue between those lanes. So you might look at these things like 4 and 2 and all of that, those little numbers with circles around them. And then the connecting tissue is those lines with the arrows on them. And each of those lines is sort of a connecting thing that says, this is still the lane, this is still the lane, this is still the lane. And what it is kind of a spline projection between the pieces of the lane. So as you listen to the next things he says, that's their goal. What they're trying to do is take this really, really dense space that is this intersection, and they're trying to reduce it down into the fundamental components that the car needs to know in order to traverse and stay in the lane, or if it needs to switch lanes, where it needs to go and how it needs to switch lanes.
So what we have is our lane detection neural network. It's made up of 3 components. In the first component, we have a set of convolutional layers, attention layers, and other neural network layers that encode the video streams from our 8 cameras on the vehicle and produce a rich visual representation.
All right, so let's start in the left-hand part of the image. You can see 3 of the 8 cameras are represented here, and there's a little ... that shows that there's actually 8 cameras, but they're only showing 3 of them, just for visual complexity's sake. But the interesting part here is, look, we've got a RegNet and an FPN. So this is basically the same thing we used to have. This is still operating in an image space and a raster space. Then it puts it through a transformer, which is an architecture that's able to do self-attention throughout this image and start to create something that's more of a vector space. It can turn the raster images into the beginnings of vector images. Then you put it through a video module, which basically syncs up a whole bunch of frames to create like a window, like a 2-second window or 60 frames or something like that. A little sliding window so that it's got video information as opposed to just still frame information. So what you can see here is that the original simpler architecture, they've used that as the front end of this whole thing, but then they've put it through a transformer and through a video module to turn this into the beginnings of vector space.
We then enhance this visual representation with a coarse road level map data.
So just FYI, this navigation map here is primarily the GPS navigation data. So this would be something that was coming directly from Google. So, when you say like, I want to go to Kroger or something, and it gives you those directions, that would be the navigation map. It's very, very coarse. And as John's about to say right here, I cut him off a little bit early, but as he's about to say, they also add in a few things that they know about these intersections and about this stuff. This is not high definition mapping. This is just information about the scene, some information about the number of lanes you would expect and all of that kind of stuff. So it gives it a bit of a clue about what's going on, but the car is still going to need to figure out where all of these lanes are and how to navigate them.
We encode with a set of additional neural network layers that we call the lane guidance module. This map is not an HD map, but it provides a lot of useful hints about the topology of lanes inside of intersections, the lane counts on various roads, and a set of other attributes that help us. The first 2 components here produced a dense tensor that sort of encodes the world. But what we really want to do is to convert this dense tensor into a sparse set of lanes and their connectivities. We approach this problem like an image captioning task, where the input is this dense tensor, and the output text is predicted into a special language that we developed at Tesla for encoding lanes and their connectivities.
All right, so this is the part that's genius, and it's also the part where I have to give myself a little pat on the back, because since May of 2022, I've actually been working on a very similar problem of taking a vision task and turning it into a language task. So I had to give myself a little pat on the back. In fact, when John was here, if there'd been a camera on my face when he came up and started talking, when he got to this part and he started talking about how they're turning it into a language problem, my jaw must have gone like Because I was like, holy crap, somebody else is working on this. I thought I was a complete nutcase about doing this. So anyway, it was very, very exciting. And this is the reason why it was such a treat to get to listen to this. Because I was like, not only am I not crazy, but there are people who are using this in a much more sophisticated way than I had even been thinking about using it for. All right, so let's start with an image captioning task. That's a classic problem, and a lot of research has gone into that. So you have an image of something like a dog, right? And what you want is the label dog that comes out of that. So you've got a really, really dense tensor, which is the input matrix of all of the pixels in RGB space. So you've got 256 by 256 by 3 because it's RGB. So you've got a whole bunch of pixels. That's a dense tensor. Out of that, you get a very, very simple sparse tensor, which just says dog. Now, that's represented in the computer's brain as a vector, and that's going to be important in just a minute. But basically, that vector can be interpreted as the word dog, which we human beings can understand. So you've taken a really, really dense thing, an image with a whole bunch of stuff going on, and what you've produced is something really, really simple. And you can start to see where this is going now, right? Just like a lane. We're taking really, really dense world space, and we're turning it into words. We're turning it into a sort of a 3D language of where things are and where they're going. And that's just genius. And just really quickly before we go on, I want to mention auto-regressive decoders. They're pretty genius. What they are is you could take a sentence like a cat sat in a hat, right? I don't know. I think I always do that sentence or something similar to that. An auto-regressive decoder, what it does is you know what the sentence is already, right? You've got that as your input. It removes the word cat. So it'll take that out of the sentence and say the blank sat in the hat. Feeds that through the network and it says, hey, what's the word that's missing? And then the network says something like giraffe or something, or grass or whatever. And the thing says, no, you're really, really far off. And then it says dog and it's like closer, you're almost there, but you're not quite. And it eventually learns that probably the best word to put there is the word cat. So it figures this all out automatically on its own. All you have to do is feed it sentences because it can automatically remove words and it can figure out how to replace those words with predicted words, and it can learn on that. So it's automatic, auto, and it's regressive. It's regressing towards a solution and it gets closer and closer to the right answer, but it can do this all very much automatically. And that's one of the reasons why a program like GPT-3 or something like that can work so efficiently, because it's able to do auto-regressive decoding. So they're able to do this with the dense tensor world. John didn't exactly say how they're doing this, but I'm assuming that they're removing chunks of the world or chunks of the predicted path that it's supposed to go on, and the neural network has to figure out the stuff that's missing. So it's basically learning on its own. And so notice from the dense world tensor that we've got in the middle of the image, when we get to the right, we get a very, very small vector called lane instances, which is just where are the lanes? How many are there? Where are they in things? And then the adjacency matrix is how are they lined up next to each other and how do they flow over spatial stuff. So much, much more sparse output, which is what you're looking for. You're going from a dense world of all this stuff to essentially a language, which is just saying lane 1, lane 2, lane 3, and it's projecting where it's going in space. And of course, if you think about the way we human beings drive, when we get to an intersection, we're not going like, oh my gosh, all of these pixels everywhere that I'm seeing. We're just sort of going like, that's a lane, that's a lane. This is the transition between those lanes across the emptiness of the intersection. That's probably the direction I want to go. So we're thinking kind of in this way ourselves. So this is mimicking what human beings are doing, and that is really, really cool.
In this language of lanes, the words and tokens are the lane positions in 3D space. In the ordering of the tokens, and predicted modifiers in the tokens encode the connective relationships between these lanes.
So you've got tokens, which are like lane 1, lane 2, lane 3, lane 4. And then the modifiers are things that tell us about these lanes. It's like, are we starting a lane? Are we continuing a lane? Are we forking a lane? Are we merging a lane? Stuff like that. So these become tokens kind of like words. And again, while they're not words, they're mathematical. And in computers, words are just mathematical things anyway. You've got programs like word2vec that actually changes a word into a vector, into a number. And that vector, that word vector, is actually the thing that transformers and language models and stuff operate on. They don't actually operate on words because computers have no idea what the word dog means, but it does understand what this vector that's associated with dog means. And then at the end, it's translated back out to be dog so we humans can read it. So this is already set up perfectly for a system like this to work because it's already mathematical. It's not actually language. And so you can easily substitute in something like lanes for words.
By modeling the task as a language problem, we can capitalize on recent autoregressive architectures and techniques from the language community for handling the multimodality of the problem. We're not just solving the computer vision problem at Autopilot, we're also applying the state-of-the-art in language modeling and machine learning more generally.
All right, I know I'm interrupting a lot, but I think it's really important to understand that Tesla is constantly looking out in the world. What is everybody doing? What is the state of the art? What kinds of things are changing? How can we get on that, and how can we produce something that's usable for what we're trying to do out of this research? And I love that they're going way outside computer vision. They're looking at language models, not just computer vision models. And again, like I said, this is something I've been working on since May in my own little project, but it's really cool to see that this is something that's actually being produced and put out in the world, and people's lives are depending on it, right? This car has to be able to navigate through really complex scenes, and it's just amazing to see that this type of system actually works for that.
I'm now going to dive into a little bit more detail this language component. What I have depicted on the screen here is a satellite image which sort of represents the local area around the vehicle. The set of nodes and edges is what we refer to as the lane graph, and it's ultimately what we want to come out of this neural network.
Okay, so just real quick, the white dots are nodes and the blue lines are edges. So basically the nodes, you can see each one represents a lane, and then the blue kind of, indicates a continuation of your driving. And John's going to actually talk about the bottom right here. So if you look at the 1, 2, 3, 4, 5, 6th across on the bottom, that node at the bottom kind of forks out into two potential lanes. So it's a right turn arrow, and you can see that you could go into two lanes as you turn out there. So we've got a forking situation here into two lanes that would then continue on.
We start with a blank slate. We're going to want to make our first prediction here at this green dot. This green dot's position is encoded as an index into a coarse grid which discretizes the 3D world. Now, we don't predict this index directly because it would be too computationally expensive to do so.
So if you look at this image real quickly, you can see we've got a tic-tac-toe board across the entire thing. Basically what he's saying is if you tried to parse out the entire scene at this level of resolution, it would just bog the computer down and it would never be able to run it even close to real time. So they've got to get a whole bunch more clever about it.
There's just too many grid points, and predicting a categorical distribution over this has both implications at training time and test time. So instead what we do is we discretize the world coarsely first. We predict a heat map over the possible locations, and then we latch in the most probable location.
So now you can see the tic-tac-toe board is much bigger, right? So we've only got a few points that we have to really look at and try to figure out. And then the heat map is just a probability map. It's like, where is a lane probably going to be located here? And where those lanes are probably located, then you start to get a more fine resolution grid that you start to project, and you start to figure these things out. So it's kind of a tree search. It starts off really, really broad and coarse, and it refines until it figures out approximately where that point is. But it only has to use high resolution in the area really, really close by where it is.
Conditioned on this, we then refine the prediction and get the precise point. Now we know where the position of this token is, but we don't know its type. In this case, though, it's the beginning of a new lane. So we predict it as a start token. And because it's a start token, there's no additional attributes in our language.
So for those who know about AI and language, this is actually something you'll probably recognize immediately. But for everybody else, there's a thing called a start token at the start of a sentence. So again, if it was the cat sat in the hat, you'd have start, which is a special token to tell it that's the start of the sentence. Then you'd have the cat sat in the hat, and then you would have end, which would be your end token. So you've got the words in between, but you've got these special tokens to tell you that it's the beginning and the end of that. And then, of course, you've got things like fork predictor, merge predictor, spline coefficient predictor. You don't have any of those because it's a start. So it doesn't have to refer back to anything. It's the beginning of something.
We then take the predictions from this first forward pass, and we encode them using a learned positional embedding, which produces a set of tensors that we combine together, which is actually the first word in our language of lanes. We add this to the first position in our sentence here.
So what these colored blocks represent is kind of an embedding space for each of these things: point predictors, topology type predictors, fork point predictor, all of that kind of stuff. They turn that into a tensor, and that tensor is sort of like the vector, the thing that represents the first word. So it's got start in there, so it understands that it's the start, but then it's got a whole bunch of things that tell it where it is in space, what it's doing, what kind of lane it is, all of that kind of stuff. That becomes a word, and then that gets stuck in at the beginning of the sentence, right? So you have to think of this. Each lane is like a sentence. It's like, the cat sat in the hat. It's that kind of a thing, right? Except that it's lane points that you're dealing with rather than words.
We then continue this process by predicting the next lane point in a similar fashion. Now, this lane point is not the beginning of a new lane. It's actually a continuation of the previous lane. So it's a continuation token type. Now, it's not enough just to know that this lane is connected to the previously predicted lane. We want to encode its precise geometry, which we do by regressing a set of spline coefficients.
Okay, so for word 2, right, in our sentence, the yellow dot, we know it's a continue token, so it's continuing on, so it knows that it's not the start or the end of a sentence. And then you're also beginning to create a spline. So they do an autoregressive thing where basically it just projects backwards and it figures out the proper curve to make from the green dot to the yellow dot, which tells the car where it needs to drive.
We then take this lane, we encode it again, and add it as the next word in the sentence. We continue predicting these continuation lanes until we get to the end of the prediction grid. We then move on to a different lane segment. So you can see that cyan dot there. Now, it's not topologically connected to that pink point. It's actually forking off of that green point there. So it's got a fork type. And fork tokens actually point back to previous tokens from which the fork originates. So you can see here the fork point predictor is actually the index 0. So it's actually referencing back to tokens that it's already predicted, like you would in language.
So here what we're seeing is a new thing, right? And I told you to pay attention to the fork. So that cyan dot is referring back to the green dot. It's like, where did I come from? That's the thing it's learning. That's the self-attention thing. And that's what's important with language. So when you look at a sentence like the cat sat in the hat, if you take away the word cat, the word sat refers back to something, and something that's sitting is generally speaking a live thing, an animal, not a vegetable. So it's going to be probably something that has mobility and stuff, so that the language model, what it does is it learns, the neural network learns that the word sat refers back to this word and that word is important to it. So here, just like that, the cyan dot is referring back to the green dot and saying, what's important? How am I connected to this thing? What's the consequence of being connected? How much should I pay attention to it? So all of that kind of stuff is based on a language model, and it's something that neural networks have been trained at and are really good at learning on their own.
We continue this process over and over again until we've enumerated all of the tokens in the lane graph, and then the network predicts the end of sentence token.
So if you look at this image, all of these white dots and everything, that's all of the sentence. It's a very, very long sentence, right? So if every single one of those nodes was a word in this sentence, it would be, I don't even know. I mean, maybe it's like 30, something like that. So it's a 30-word sentence, but then at the end of that, you get the special token end of sentence, which means that it's completely predicted the lanes and it's completely predicted how they're all connected. So it's like, aha, I'm done. And now we can move on to the next task, which is actually driving through this scene.
Yeah, I just want to note that the reason we do this is not just because we want to build something complicated. It almost feels like a Turing-complete machine here with neural networks, though, is that we tried simpler approaches. For example, trying to just segment the lanes along the road or something like that. But then the problem is when there's uncertainty. Say you cannot see the road clearly, and there could be 2 lanes or 3 lanes, and you can't tell. A simple segmentation-based approach would just draw both of them. It's kind of a 2.5-lane situation. And the post-processing algorithm would hilariously fail when the predictions are such.
So this was actually one of my favorite moments of the entire evening. Ashok Elluswamy actually, kind of interrupts, and they have a little conversation here. And this was the thing where I was like, oh, if I could only wander the halls of this place on a daily basis and listen to people talking about these things in even more detail, it would just be fascinating to hear that stuff. But basically what Ashok is talking about here is that they're not trying to do something complicated for complicatedness' sake, right? They didn't just go like, oh, let's take a relatively simple architecture and turn it into something really complicated, only to make it simple at the end. He was like, nothing else was working. They tried all of these different things, and they're like, how are we going to model these incredibly dense, complicated intersections? And the language model was the brilliant insight. I don't know if it was John or Ashok or somebody else on the team, but somebody had this insight that they could use a linguistic model and they could model these lanes as sentences.
Yeah, and the problems don't end there. I mean, you need to predict these connective lanes inside of intersections, which it's just not possible with the approach that Ashok's mentioning, which is why we had to upgrade to this sort of...
Yeah, when it overlaps like this, segmentation would just go haywire. But even if you try very hard to put them on separate layers, it's just a really hard problem. But language just offers a really nice framework for getting a sample from a posterior as opposed to trying to do all of this in post-processing. But this doesn't actually stop for just autopilot, right, John? This can be used for Optimus.
All right, so you heard what he said, so pay attention to this next part, right? We've got, this is not just for lanes. Once you create an architecture like this, you can use it for a whole bunch of different purposes, including a robot walking around a room or a factory or something like that, as opposed to somebody driving in a vehicle.
Yeah, I guess they wouldn't be called lanes, but you could imagine, sort of in this, stage here, that you might have sort of paths that sort of, encode the possible places that people could walk.
Yeah, it's basically if you're in a factory or in a, home setting, you can just ask the robot, okay, please route to the kitchen or please route to some location in the factory, and then we predict a set of pathways that would, go through the aisles, take the robot and say, okay, this is how you get to the kitchen. It just really gives us a nice framework to model these different paths that simplify the navigation problem for the downstream planner.
All right, so ultimately what we get from this lane detection network is a set of lanes in their connectivities, which comes directly from the network. There's no additional step here for sparsifying these dense predictions into sparse ones. This is just a direct, unfiltered output of the network.
So this is worth mentioning as well. The fact that we don't have to do any more processing is absolutely huge, right? So the output of the network itself is already a sparse language, a sentence of lanes that the car can then utilize to traverse that sentence or that lane diagram, and it can figure out where it needs to go. So there's no more processing that has to happen after this. You get the result that you want automatically by using this linguistic model. John then goes on to talk about object detection and kinematic prediction and things like that. But this video is already long enough and we've just talked about lanes. But anyway, I hope you can see how amazing what they're doing is here. And the amazing part is not even the fact that they came up with a solution, but the fact that they're looking afield. They're looking into other disciplines. They're looking away from vision directly. They're looking at language. And ultimately, data is data. A sentence is data. Vision is data, sound is data, all of this stuff is data. So you can use all of those things, and if you're clever enough, you can kind of cross-pollinate between different disciplines and come up with miraculously cool solutions like what they have here. And again, as I said, this was my favorite part of the entire evening. This was the thing that just made me so happy to be there and to actually be able to see what's going on and how clever outside the box thinking can solve problems that might seem really intractable. All right, I hope you enjoyed this episode and found it fun and interesting and thought-provoking, and again, very, very geeky. I hope I tried to explain kind of how this is all working and why not just the solution, but the methodology for coming up with the solution was so important and really shows us how amazing Tesla's engineers truly are. Anyway, if you did enjoy the episode, please do like it because the YouTube algorithm depends on that, and of course, consider subscribing for more of this kind of content. As always, a huge shout out to my patrons on Patreon. Thank you all so much. Again, I couldn't have gotten to AI Day without your support, so I really do appreciate it. I appreciate the emotional support. I appreciate the conversations. And again, don't forget that I'm going to be in Florida on the 21st and 22nd at TeslaCon Florida. So check out the information in the description. I'll leave it down there as well. And hopefully I'll be able to see you all in person there. And of course, if you want to join the Patreon team, just check out the link in the description. And if you're interested in a whole bunch of really cool merch, check out our merch store. Link is in the description. We have TeslaBot t-shirts, the Tesla meme t-shirt, Success is a Possible Outcome, 4680 battery cells. All of that stuff is on t-shirts, mugs, tumblers, and on and on. So check it out. And for those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Thank you. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a solar roof, a Powerwall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.